Today we'll be solving another truss using the method of sections. So without any more chat, let's get to it. So this is the truss that we're going to be solving. You can see here there are quite a few members in this truss. We've got 7 joints, we've got 2 supports, a pin support at A and roller support at B, and we've got these 3 external point loads. We've been tasked with finding the internal forces in member 2-4, so this member here, member 3-4, this member here, and member 3-5, this member here. The easiest thing to do would be to create a cut just through these 3 members, and as a reminder, we can only cut 3 non-zero force members, so this works out very well for what we need to do. So now that we've seen the truss we're going to solve and we know what we're going to do, let's start off by finding the reactions. So to find the reactions, I'm first going to substitute the supports that I have here with the reaction forces, thus creating a free body diagram. So we'll start off with A. I've got a pinned support here, and therefore I will have 2 reaction forces, AY and AX. And at B, I've got a roller support, which will lead to 1 reaction force of By. I am going to start off by summing up my forces in the x direction, with this being my positive direction. And in this case, I've got Ax and nothing else, so Ax has to equal 0. Moving on, I am going to do moments around A. And the reason I'm choosing to do moments around A is these 2 reaction forces, this one here and this one here, will not contribute to moment around A because they pass through it. And also this 15 here also passes through A, so will not contribute a moment. So in this case, I've got By creating a positive moment with a distance of 12. I've got the point load of 5 creating a negative moment also with a distance of 12, and I've got the point load of 25 creating a negative moment with a distance of 6. This gives me 12 By equals 210, and if I divide everything by 12, I get that By is 17.5 kilonewtons. And the last thing that I need to do is the sum of forces in the y direction, with this being my positive direction, and in this case I've got Ay plus By minus those 3 concentrated loads, so minus 15, minus 25, and minus 5 equals 0, so that works out as Ay equaling 45 minus By. Luckily we've just found what By is, so that would be 45 minus 17.5, leaving me with an Ay of 27.5 kilonewtons. The prudent thing to do here would be to check. I can do this by doing, for example, moments around B, just to verify my reaction forces. Once I've done that, I will replace the forces with their actual values. So Ax was 0, so I can just eliminate that. Ay was 27.5, and By was 17.5, both positive, so I assumed the correct direction for both of them. Now that I have the reaction forces, I can move on to looking at that cut we discussed earlier and finding those internal forces that I need to find in the truss. Let's do it. Okay, so I have drawn the cut that we discussed, and the first thing that I would want to do is I want to decide if I'm going to look at the right-hand side of the truss or the left-hand side of the truss. In this case, I'm going to go with the left-hand side, and that is just because there are less forces on it. So the reason that you choose a certain side is just easier geometry, less forces, anything to make it an easier calculation, because regardless of the side you choose, you will end up with the same forces. So what I'm going to do now is just draw out that left-hand side. I'm going to put all those internal forces that I've now exposed in tension, so arrows coming out. So N35, N34, and N24. I'm going to add my external force of 15, and I'm going to add that reaction force of 27.5. And the other thing that I want to do is I want to add the angle here, because it's obvious to me that I'm going to use it. It's 45 degrees, and we can see this by looking at this triangle here, where we see that we've got 3 on 3, giving me an angle of 45. So now that I've got that, I want to think very carefully about what equations to use. Now I can see that if I look at the x direction, N35, N24, and N34, or a component of N34, all have forces in the x direction. So I'm not going to be able to find anything at this point. However, if I look at N34, N34 has a component, an unknown component currently, in the y direction, and that is the only thing that I don't know in the y direction. And that is where I'll start. So sum of forces in the y direction equals 0, with this being my positive. As I said, I've got a component of N34 going in the positive y, and that will be cos 45. I've then got a negative 15 from that point load and plus 27.5 from the reaction. And so if I isolate that N34 cos 45, I get that that equals minus 12.5. And to get N34, I need to divide that minus 12.5 by cos 45, and I end up with minus 17.67 kilonewtons. The minus means that I've assumed that this is in tension. It's actually working out negative, meaning it is in fact in compression. The next thing that I want to do is I want to take moments around joint 3. This is joint 3. And the reason I want to do that is because I can see that N35 and N34 both pass through joint 3, so they're not going to contribute to a moment. The only thing that I don't know that will contribute to a moment is N24, so I'll be able to find N24. So starting off with sum of moments around joint 3 equals 0, with this being my positive direction. And here I've got minus N24 times 3, so that's a negative moment. The 15 contributes a positive moment with a distance of 3, and the reaction of 27.5 contributes a negative moment, also with a distance of 3. And if I isolate N24 and sum everything up, I get that N24 equals minus 12.5 kilonewtons. So once again, I got a negative value, which means that this is in compression. Moving on, I'm left to find N35, and the best way to do that is actually to continue these lines and to arrive at joint 4. And by doing that, N34 passes through joint 4, N24 passes through that point as well, therefore not contributing to moment. It doesn't matter that joint 4 isn't on this little bit that I've drawn, because I can do moments wherever I want. Just geometrically, I know exactly where joint 4 is, and I know exactly what passes through, which makes this easier. So, sum of moments around joint 4 equals 0, with this being my positive direction. And here I've got N3, 5 times the distance of 3. The 15 contributes a positive moment, but with a distance of 6. And the 27.5 contributes a negative moment with a distance of 6 as well. So 3N35 works out as 75. And if I divide everything by 3, I end up with N35 being 25 kilonewtons. Now, since this worked out as positive, it means that my assumption was correct and it's in tension. There is one last thing that I want to do, and that is a check, just to make sure that these all make sense. And I'm going to do the check by summing the forces in X. So in X, I've got N35 and N24, and a component of N34, so that works out as N34 sine 45, and they should all sum up to 0. So let's check that. We've got 25, and then N24 gives us minus 12.5, and N34 is minus 17.67 sine 45, and if we calculate that, that indeed works out as 0, so that means that this check is correct. And that's it. We've found the internal forces in the members that we were tasked to using the method of sections. As you saw here, it's good to be strategic when choosing the side that you're going to calculate and analyse, and also the order and where you're going to analyse the structure. So in this case, we found that doing moments around two specific points worked really well for this truss, and also deciding where to do forces and what checks to do. I hope you'll join me again for some more structural engineering. And in the meanwhile, bye for now.